Hi, everyone. I don't speak Portuguese. Sorry about that. So today I'm here to speak a little bit about deep learning and the Spark Deep Learning's package, and also a little bit about managing your machine learning lifecycle and modeling with our new open source project called MLflow. So a little bit about myself. I'm Raela Wang. I'm a solutions architect at Databricks. Has anyone heard of Databricks before? So you guys Spark users? No. Okay. So Databricks is the company behind Spark. So we love Spark. So the whole presentation today is going to be Spark, Spark, Spark. So the agenda today is, a little bit about deep learning frameworks out there, the ecosystem. How does Spark help? It doesn't actually help natively in Spark, so you have to rely a lot on Spark packages out there. And how we can use deep learning pipelines to make it really easy to get started with deep learning. And I'm going to do a little demo of identifying suspicious behavior in CCTV footage using the deep learning pipelines library. Then I will touch upon MLflow, how we can use that to manage the whole machine learning model lifecycle, another demo, and then we'll close off with a roadmap and Q&A. So, who does deep learning? Couple of hands. So, deep learning is gradually becoming really popular. There are a lot of open source frameworks out there like TensorFlow, Keras, PyTorch, and it's getting really popular recently because compute power is getting cheaper and people can get their hands on larger instances for compute. So why is it hard, and why is why is it not super mainstream now compared to, say, linear regression and all of that stuff? So, it requires a lot of expertise. The learning curve to actually get started with deep learning is steep, and it requires, I think the second point there, it requires many engineer hours. So the reason for that is the low-level APIs. So it's kind of similar to how Hadoop MapReduce was for big data back in the day, 10 years ago. And you have to write a lot of code. You have to learn how to use the APIs, and you have to code like 100 lines for a simple word count application. Whereas Spark today is just .map.reduce. So it's really hard for people to learn the APIs and get started with deep learning. So how does open source Spark help? Not very much. So we have multi-layer perceptron within Spark MLlib, but we don't have the cool neural networks and stuff like that. So it's really relying on the ecosystem out there. Big DL, Deep Learning for J, those are the packages that are built on top of Spark. So we're going to touch upon how we saw a pattern with MapReduce back in the day and how deep learning is right now. And we rolled out this package called Deep Learning Pipelines. It's open source, so you can always pip install or whatever and try and get your hands dirty and try deep learning. So it focuses on the ease of use and integration. Ease of use, meaning that it's kind of like, if you use scikit-learn today, it's really easy to use. We've built it such that it integrates with Spark MLlib. So you can, say, use a deep learning transformer within your MLlib pipeline, and it's really easy to get started. There are little code snippets you can get started with. I have a demo really soon, and it's literally like a few lines of code just to get a popular deep learning, model out of 5 lines of code. So transfer learning. Transfer learning is kind of like using a pre-trained model, and that's the easiest and fastest way to get started with Spark deep learning pipelines. So here we see a simple example. We import the package, and we are using the deep image predictor. And we are using the Inception v3 model, which is a pretty popular model trained by Google. They've trained this model on huge amounts of images, and it's really good for identifying objects in images. So we're basically loading the inception v3 model, and then we're just calling a dot transform on your image data frame, and that's it. You have like all the predictions, and it looks kind of like this. And you can see that that's the file path for my image on the left, and then the results saying, you know, this is predicted to be a daisy, an ant to be, and the probability of that object being in that image. And that's 4 lines of code. So it's really easy to get started. I would say it doesn't require a lot of expertise. There's also the option to train your own deep learning model, say with Keras, and you can save that, and you can also load it into this package, and then use your model to generate predictions on large Spark data frames. So it's kind of like distributed predictions on your pre-trained Keras model, for example. Demo time. This is Databricks, and I will be using Databricks for the demo. So here I have my cluster running, and what I did here was I just spun up a ML beta runtime. So this image on Databricks contains all the deep learning packages I need. So all I need to do right now, since I have my ML beta runtime cluster up and running here, is I need to attach a few libraries in order for it to work. I need the OpenCV package. Let me attach that. Okay, it's already attached. And then I also need the MLflow. Can't find. Gonna install MLflow right now. Bye. Okay, so it's attached. So I can start my demo. So what I'm going to do is I'm going to look at one of my notebooks I have here. And in this notebook, I'm just going to attach it to my cluster. Did it auto-terminate? So I've managed to attach it to my cluster. I just had to refresh the screen a little bit. So in this pipeline, what we're going to do is we're going to load in the videos that are in S3. We're going to do some pre-processing. So in this pre-processing step, we're going to extract JPEG images every second in the video. And then I'm going to pass the JPEG images into my deep image featurizer. And what I'm going to do is I'm just going to use the transfer learning API we saw earlier. I'm going to load in the inception v3 model, and I'm going to use that to transform and generate my features from the JPEG images. And I'm going to use those image vectors and put it through a really simple logistic regression model with Spark ML. So this is a live demo. Fingers crossed it works. So first step is I'm importing some functions that I have defined earlier, and I'm just going to show you what that looks like. So it's really some helper functions to get my videos and my images to display like a pretty display for my videos and images in my notebook. So it's kind of like a HTML. I'm displaying like a HTML thing in the notebook. Hopping back. So what I did was I import those helper functions into my current notebook once it loads. This is Nubank Wi-Fi. It's not Databricks. So, okay, hold on, I'm in the wrong notebook. Okay, so I imported the functions I needed. So I'm gonna do an ls command here within my notebook to see what all the files I have in S3. So these should be, the MPG video files I have. And let's take a look at what one of these videos actually look like. So I'm running my, HTML code here. So I'm calling that function that I predefined, and I'm putting in the path of one of these, videos, and then this should play once it loads. Again, it's the Wi-Fi. There we go. So I have a whole S3 directory full of these videos. They are kind of acted out by someone else, and I took them from an online source. And so it's kind of like emulating CCTV footage of a room. So the camera is not going to move. It's always like this, and then we have like people walking around. And then what we're trying to do is to pick out suspicious activity, such as people fighting or picking a fight and then like leaving unattended baggage. So it's kind of like at airports you don't really want to have people leaving their luggages somewhere and then maybe no one's monitoring the screens or something like that. So that's the kind of use case we're targeting here. So what I'm going to do here is I'm going to use OpenCV to kind of extract the video frames. So here I have it here. It's every frame per second. I'm going to run this. What I'm doing here is I'm just extracting the frame from the video, save it back into S3, save the JPEG into S3, and then go like to the end of the video and then go to the next video. So I'll have a lot of images per video. So you can see that I'm saving that out into my S3 location again. So the next pre-processing step is to kind of like dropping the nulls in case we have any images with like size 0. I'm just scrolling down. Looks like we don't really have any visible, but I'm just going to run this anyways. So I'm just dropping the files that have 0 file size. Run that. And now we're going to use Spark to load the images in. So from Spark 2.3, we support images better than Spark 2.2. We add a new API that says, read images. So this is a native Spark API. And I'm just loading the whole training, folder that I have. So it's a series of different images. I'm just going to run that right now. And yeah, Spark will handle all of that for me, and it should distribute across my cluster in parallel. And the next step is, I'm just going to line this up. And the next step is importing the Spark Deep Learning Pipelines library and using the Deep Image Featurizer, which we briefly saw in the presentation. And again, here's the Inception v3 model. So this is taking a little bit of time. I probably should increase the number of partitions. Okay, so we can see that we finally loaded the images, and if I scroll really fast, it'll be like a video, but it's basically a sequence of images that I have in the video. And if I expand this, you can see that it's loading in as binary files. Cool. So here we can see that my deep image featurizer thing ran. And what it did is it basically pulled in the model from somewhere from the internet, and then we are using that model to transform my image data frame, which is what I just loaded here. And then what I'm going to do is to write that out into S3, so persisting the data set I'm using for my modeling. So I'm writing out the image data frame. Actually, no, I'm writing out the features out as Parquet files back into S3. I'll just leave that to run. So the next step is to do the fun modeling. So in the previous notebook, what we saw is loading the videos, extracting images from the videos, doing some light pre-processing, like dropping the images with file size 0, and then we passed it into the session v3 model. And then in this notebook, what we're going to do is to train the logistic regression model to pick out, images where we have suspicious stuff going on. So what I'm going to do is to load that data back from S3 where I wrote out from the previous notebook. And I'm doing a join with the labels. So if you're wondering and if you're curious, what I did here is I actually hand labeled each image one by one and saved it out as a CSV file. So in practice, obviously it's a logistic regression is supervised learning. So for supervised learning, you have labels. So in this example, what I had to do is I had to hand label each image one by one. Not very fun thing to do, but after that, I'm just doing a join for my features and my labels, and then I'm using that as my training data set into logistic regression. So that's what I'm doing here. I'm using Spark to join the two data frames together. Now what I'm doing is I'm loading the logistic regression model from ML, Spark ML, and that's the data frame API for Spark MLlib. And I'm going to train a logistic regression with very random parameters that I've grabbed from nowhere. I'm just putting random numbers here and hope for the best. And then what I'm doing is I'm fitting it on my training data set. What I can do is I can save that model out into S3 as well, so persist the model that I just trained. I'm not going to do that because it takes some time. And in this step, I'm just loading the model that I trained before back into my session, and I'm going to transform it on my test data. And that worked. So what we've seen was in that few lines of code, I've done the featureization with deep learning, and now I'm moving on with my image vectors and passing it into a logistic regression model. I trained the model with Spark, and I generated predictions with the test data set. So let's see how our model did based on just picking random parameters that I passed into logistic regression. So what I'm doing now is I'm going to look at the result data frame, and I'm filtering for where prediction equals to 1. So that's where it's predicted to be suspicious. So if I look at my file names, I actually, in a previous notebook, I named each image in a way where I retained the video name, so I know what video it is. So in this one, it actually left a bag at a chair, so that's pretty good. And you can see that it picked out a whole series, which is what we would expect. This one left a box. So it's actually pretty good. I didn't use any evaluation metrics, but I can always import, say, a binary classification evaluator and evaluate my model. So what I'm going to do here is I'm just going to take a look at one of these images. So I'm doing that here. It just looks interesting because it says fight. So I'm just going to see what happened there. So that's the image with one person lying down on the floor. So that's pretty good. That's a good sign. So let's take a look at a video for this particular image. Nubank Wi-Fi. See a couple of people walking around, and then these two guys just pretend to fight, but it's pretty convincing. So our model managed to pick this up as suspicious, which is pretty good for a logistic regression. And we managed to do a really simple, image detection toy project with the deep learning pipeline library and, simple logistic regression, which is pretty cool. So back to the slides. Now we're going to look at how we can manage the model development lifecycle with MLflow. So what we did in the previous activity was we did simple training, like experimentation, and in real life, I'm sure you guys know better than I do, we have to iterate on this multiple times to look for the best model before we put something into production. So what we're going to talk about is ML model development challenges, how MLflow tackles these challenges, and then I'm going to do a really quick demo on what MLflow looks like. We all know that's true. So ML lifecycle, we have raw data, we prep the data, we train, we deploy, and we have to keep going in a cycle. We iterate, and we run this multiple times. At every stage, there's multiple different tools that we use. For raw data, you're using different various data sources, maybe Hadoop, MongoDB, some S3, for example. Data prep, maybe you're using Spark, maybe you're using scikit-learn, Pandas, whatever. So there are multiple tools that you're using. Training, it could be XGBoost, TensorFlow, again, multiple, machine learning frameworks that you're using. And then deploy, you could be using Docker, you can be using like SageMaker, you could be using Spark for batch predictions. So there are multiple tools at every step of the ML lifecycle. And at these two particular steps, for the data prep and the data training, you'll be doing like hyperparameter tuning, you'll be running it again and again and optimizing it for the best, models. And at each point, at some point, you will want to scale that so that you're not only running on your own laptop, you want to maybe run it remotely on remote machines. So model governance comes up. How do we track your model experiments? How do you iterate on those? How do you reproduce them? How do you make sure that, if we pass it to someone else, they are able to regenerate the same model that you created? So to recap, what are the ML development challenges we noticed? So there are lots of software tools we can leverage for storage, for ETL, for data prep, for the modeling. And then it's hard to track and reproduce those results, and it's hard to push those models to production. So that's the motivation behind MLflow. Our engineering team decided that it's a recurring pattern among our customers, and we've decided to, create a project. We open sourced it, and it's called MLflow. In theory, it should work with any ML library, and any ML framework, any language, Python, Scala, anything, and it should run anywhere. It could run on your local laptop, or it could run in the cloud. And MLflow today has been designed to run from 1 to 100,000 data scientists on the same platform. So if you have more than 100,000 data scientists, sorry, but it's not gonna work for you today. We're working on that, but you might have to spin up like multiple MLflow instances for that too. So today it's designed to work for 100,000 data scientist organization. So the design philosophy was API first. So it's, we have open APIs, we have a CLI for you to, push any model, any language into MLflow. And it doesn't even have to be a machine learning model. It can be a Lambda function. It just has to be something that you want to track and recreate. And we made a really modular design. So there are 3 components: tracking, projects, and models. And you don't have to use every component. You can pick and choose whatever you need. So it's a really modular design there. So looking into individual components, MLflow tracking, which is really for you to record, what data set you use, what algorithm you use, what version, what library version dependencies, which is usually a nightmare, and also the results of all your ML models. Projects is kind of like packaging that up so that you can deploy the same thing into production really easily. And models, which is, how do you integrate your packaged model into your deployment workflow. So MLflow tracking, which is the first component, and it's also the portion that I'm going to be demoing today. You can run your code from anywhere. It could be notebooks, your local laptop, in the cloud. you push everything into MLflow, this thing called the MLflow tracking server. You can have the MLflow tracking server running on your laptop. Just go to your browser and look at localhost, and you can have your own laptop version of MLflow there. Or you can launch it on, say, EC2 on AWS and have it for the whole team. And then from MLflow, we have a UI in the browser for you to consume the results, or you have an API to query and look at the results there as well to consume, query the results from there. So that's tracking. The key concepts of tracking is to log everything that's essential to your model. So things like what parameters you passed into the model, the error metrics, artifacts, which includes the model itself. So it's like saving that model into S3 so they can load it back or save it into whatever cloud storage you have. And then also what source code, so exactly which Git hash you used, for example, to generate that model on that particular data set. So the next component is MLflow Projects. And the idea here is to package everything up. So the code, the configs, the data, library dependencies into something we call like a project file, a project spec. And then you can push that into, deploy, to run on a local machine or in the cloud. So the MLflow project looks something like this, where we will have something called the project file. Right at the top, you have the conda environment. In this case, we have a conda YAML file, so all your Python dependencies, system dependencies, they go in there. And then we have the training data path. So the path to your data, training data. So a snapshot, code, and things like the lambda parameters, so the actual model parameters that you're passing in, and the actual command you ran to run that machine learning model. So you can do that. You can do this whole thing with the CLI, MLflow run git and then path, or from a Python API, so mlflow.run. MLflow models, which is the third component of MLflow, is you have multiple sources coming in, multiple sources from your notebooks, again, from locally or from the cloud, and you're using different model frameworks to train your models. So for example, you could have TensorFlow, you could have scikit-learn, you could have Spark. So you're using different machine learning frameworks to train your model, and then you have different various deployment tools. So for example, you might package your scikit-learn model and deploy it with Docker and Python, or maybe you have a Spark model and you're using like a structured stream to score it with an in-memory model, or you could have something like SageMaker and you just want to push it with a REST endpoint. So there are different tools, deployment tools. You might have lots of these. And the idea of MLflow models is that you have a common format and you have a central point to connect to those various deployment tools, and one place for all your various machine learning framework models. So this is an example MLflow model file. And in this example, you have a saved TensorFlow model. So if you look at the directory structure, yep, there's the estimator folder and a save model.pb file. That's the saved TensorFlow file. And if you look at the MLflow model text file, you have two different flavors. You have the TensorFlow flavor, and you also have a Python function flavor. So, TensorFlow could be serialized into a PB format, and you can use the TensorFlow flavor to load it into something that isn't running Python into any system, and then run your predictions there. Or if you're loading it into a Python, Python environment, you can load it as a Python function. So the MLflow model file will handle it for you, and then when you run it in your deployment system, it will just pick up like whatever you need, and then deploy a model that way. I kind of skipped ahead. So, demo time. So previously, we looked at the logistic regression model, and what we wanted to do and what I wanted to show you is how we can incorporate that into an MLflow environment. So what I did, again, this is in a Databricks book, is I've indicated a MLflow experiment ID. And within my logistic regression code, what I did was I just wrapped it into a function. I did the very horrible thing of saying your training data equals your test data. Don't do that in real life. I'm just doing it for demo reasons. But what I wanted to do here is to start an MLflow run. And then here I have my regular logistic regression code from Spark. I'm putting it into a pipeline, fit it on my training data, transform on my test data, but in this case, it's secretly my training data is the same data set. And I have different metrics that I'm using. Eval metrics here is really area under ROC and accuracy from Spark MLlib. And what I'm using MLflow here is I'm using the log param to keep track of the max iterations I have passed in, log param for reg param and log param for the elastic net param as well, just so that I have, keeping track of all the params I used and the error metrics that it generates. And then I have log metric for the evaluation metrics. I'm also saving the model out into S3 with the log model. And then with log param, again, I'm saving the snapshot of the training data that I used to generate that model. So if I run this, I might have to run this. So now in this cell, what I'm going to do is run the train suspicious model function that we just looked at, which packages all the MLflow APIs. It starts an MLflow run. It logs everything, the params, the metrics, the model itself, as well as the data set we used. And then as I'm doing this, if I hop over to my MLflow UI, and this is the tracking server, which could be on your local laptop or your remote AWS CC2 instance, or anywhere you can launch an instance and launch your tracking server on. So here I have my ML Meetup experiment, and I'll be able to see all the various runs I've did, and who did it, the source code I did. So this will only appear as a Git with a Git hash if I've packaged it up as a ML project and then run it as an ML project. For me, what I did was I ran it from a notebook, so it's not going to show. It's going to tell me where the data is and all the metrics that I've tried before and the accuracy. So for example, if I want to compare this run with this run, I can just select it because I saw there's a little difference, and then I can say compare selected, and it will tell me exactly when this was trained, the run ID of this MLflow run, and various metrics I have, as well as a UI with a error metric visualization. And I can also download these as a CSV file, although all of these will be logged within this artifact location anyways. It's going to be in S3. So that's MLflow, and that's all I have to show for MLflow today. This is the tracking server. You can also use the project component to package it into a way that you can easily pass it on to a different data scientist or a different team for deployment. And there's also the MLflow model component, which is really an integration to your different deployment tools and deployment services. So who actually heard of MLflow before? We announced it a couple of months ago, so it's really, really new. Nobody, which is good. Now you've heard it before. Give it a try. It's open source. So we have a roadmap. It currently does not support R and Java. It does support Python really well. So if you're a Python user and if you use scikit-learn, XGBoost, you can give it a try. And we don't support hyperparameter tuning now. We definitely plan to. All data scientists use hyperparameter tuning. So yeah, things like grid search, multi-step workflows, those will be available in the longer, it's on the longer term roadmap. And It's open source, so feel free to contribute to MLflow. There's a mailing list, and there's also a Slack channel if you're interested in joining. We have quite a few people on the Slack channel. It is an open source project that we are looking at really closely, so it's a lot of activity and a lot of stuff going on right now. If you have any issues with MLflow, you can post it to the Slack channel, or you can feel free to just open an issue in GitHub. Someone will jump on that really quickly. So just to wrap up, what MLflow will help with is really the hope of this whole project, and the motivation behind this whole project is to ease the model development lifecycle, to make sure that you're able to package up your ML code, to make sure that you can track and reproduce the results. So it's really around model governance and also for model deployment. And it's open source. That's all I have. We're running Spark Summit in London, and that's October 2nd and October 4th. I have a discount code. If you use my name and 30 behind it to sign up, you get a 30% discount. Just saying, no pressure. You don't have to go. If you have any questions about MLflow, about Databricks, about deep learning, don't email me, email Shelby. Shelby is right at the back of the room there. She's waving. So email Shelby. She also has business cards on the table back there, so feel free to get one and hit her up, send her emails. That's all. Any questions?
Bom, se vocês tiverem pergunta, podem levantar a mão, eu levo o microfone até vocês.
Hello. In the first example, you showed like a constant learning, right? And if I get right, you only trained the logistic regression, not a deep learning training.
Yep.
Yeah, but it's possible with this Databricks deep learning framework to train to update the world network, okay? My question is how much speed up, how much overhead do I have when I use like Databricks clusters with Spark?
To train a distributed deep learning model?
Yeah.
It really depends on what algorithm you're using. I know it's not an answer you're interested in hearing, but it really depends on like what algorithm you're using in a data set, and how complicated
like training
it is.
Inception.
Sorry?
Like train the same architecture you showed, like Inception.
Like Inception?
Yeah. A deep network like Inception.
So Inception was a pre-trained model.
Yeah, suppose I want to train Inception in Databricks in a cluster. In this case, like, you have an idea? How much do I have in speed up?
It really depends. So based on my experience working with our customers, deep learning, like distributed deep learning would usually take a longer time to run. So it can be quite a few hours if you're trying to train your own version of Inception v3. So it's really on the data set size and the complexity of the algorithm. If your data actually fits on one machine, so you don't have to like use multiple machines, then definitely using one huge GPU to do the training would actually be much faster than, say, distributing it across multiple GPUs. So again, it kind of depends. If your data set is so big that it can't fit in one machine, then you kind of have to like use distributed training. But it does take some time.
Okay, thank you.
Mais alguma pergunta? Mais alguém? Não? Ok.
Should I say it? If people are shy, I'll be hanging around after the whole meetup, so feel free to look for me and we can have one-to-one Q&A.
Okay. So thanks, Raela, for the presentation.
Thanks.